Hi, I'm Stefan Jansen, the author of Machine Learning for Trading. In our new course, From Research to Production, I want to teach you how to take a trading idea and turn it into a validated strategy that you can actually deploy. Let's take a closer look at what that means in practice. Just like the third edition of the book, the course is organized around the Machine Learning for Trading workflow. This workflow is built around a strategy research loop supported by robust data infrastructure. It starts with a clear definition of the research objective and the constraints of the strategy, the asset class and universe, performance goals, risk tolerance, trading costs, liquidity constraints, and the intended holding period. Once these parameters are clear, we define the machine learning task. That means engineering suitable labels and features, developing and evaluating models, and then designing a trading strategy that uses the model predictions. A key point is that we draw a clear line between model optimization, strategy design, and strategy evaluation. The goal of evaluation is not simply to show attractive historical performance. It is to produce evidence about how much confidence we should have that performance when we consider the strategy for deployment. This workflow is not a straight line. It is an iterative cycle. And much of the success in machine learning for trading comes from making that iteration productive, disciplined, and efficient. That is exactly what the course is about. It is not about learning how I implemented a case study that already exists. It is about taking a case study, working within the workflow, diagnosing where the strategy can be improved, and then designing and testing targeted changes. So the course is not only about learning concepts. It is about applying them to real-world data, learning how to improve a machine learning-based strategy, and taking it toward production. At the heart of the course and the book are 9 case studies. In the book, we take these case studies through an initial version of the full pipeline. In the course, the goal is for you to take at least one of them further. These case studies cover real market settings across different asset classes. We work with US equities and ETFs, US equity options, futures, FX, and crypto futures. The data ranges from intraday and minute level data to monthly data, and time periods and number of symbols also vary substantially. That gives you a rich empirical basis for experimenting with different strategy design choices. And of course, if you have your own data and your own strategy idea, you're more than welcome to work on that as well. The workflow starts with strategy definition, not with the model. That is important. If we start with the model, it is very easy to go on a broad fishing expedition. Instead, we first need to identify the kind of edge that we have in mind. We specify the tradable universe, the cost assumptions, the liquidity constraints, and the kind of holding period that might realistically work. Based on expected returns and trading costs, we can begin to understand which holding periods are viable. We can also identify the constraints and frictions that need to be built into our research process and into the historical simulation. That matters because those are the same constraints we will face in live trading. If we do not model them during research, the strategy may look attractive in a backtest but fail when exposed to the real market. We then spend quite a bit of time on financial data as critical infrastructure. We look at the market mechanisms that shape the data we receive and use for research, and at how order flow reflects demand, supply, liquidity, and the incentives of market participants. This is the environment in which the strategy will ultimately have to operate. That becomes especially important when we later model execution fills, order state, and realized returns. Even at lower frequencies, execution and liquidity matter because the prices at which you buy and sell have a direct impact on your realized performance. The course covers market data, fundamental data, and alternative data in great detail. We also look at synthetic data and recent progress in using modern techniques to generate realistic financial data. Once we have defined the strategy, the constraints, and the available data, we can define the learning problem. That starts with labels. Labels pin down the predictive target. They determine what the model is actually trying to learn. We then look at features across several families: financial features, momentum, volatility, etc., model-based features, from hidden Markov models to Kalman filters, language-based models, and others. We evaluate these features carefully using statistical methods that adjust for multiple testing. This is quite important because false discoveries are very easy to produce in finance. If we test enough features, enough labels, enough universes, and enough model variants, some of them will look good by chance. So we need methods that help us distinguish genuine evidence from search-driven artifacts. We also discuss causality. It is important to think in terms of causality and not only correlation. In finance, causal claims are difficult because controlled experiments are rarely available. But it is still important to understand under which assumptions we can estimate causal effects and how we can try to refute causal hypotheses using appropriate methodology. Only after we have defined the research objective, the strategy context, the labels, and the features do we start working on machine learning models. We begin with transparent baselines, often linear models, because they are easier to understand and harder to fool ourselves with. From there, we move up a ladder of increasing complexity. We work with models that excel at tabular data, such as gradient boosting, and more recent neural networks designed for tabular data. We study deep learning for time series, including temporal transformers, state space models, and foundation models. We discuss latent factor models, which have become important in finance because they try to embed domain knowledge about the factor structure of returns into the learning process. The main message is simple. More model capacity is only useful if it beats simpler models in a way that survives careful evaluation. That is an empirical question. It is not something we should assume from a leaderboard or from the popularity of a model class. We also cover causal machine learning in more depth. Here the question is not simply whether a model predicts returns. It is whether some of the drivers we identify may have a causal effect on returns or on other financial outcomes. We look at several designs, including continuous treatments, discrete events, and causal discovery, where the goal is to learn what kind of causal structure might be present in the data. This is a challenging topic, but an important one because it helps us to become more precise about what kind of evidence we really have. Another major theme is that research itself should be treated as an experimental system. Every attempt we run is an experiment. Every feature set, label definition, model specification, universe, and backtest variation contributes to the search process. If we do not track these trials, we cannot properly account for the search cost. So we develop code to track experiments and make results reproducible, comparable, and countable. This is what allows us to adjust for multiple testing and to understand how much of the observed performance may be inflated by repeated search. This is also what makes the research process more auditable. We can see what was tried, what worked, what failed, and how much evidence we really have. Backtesting is another central part of the course. We treat a backtest as a historical simulation whose purpose is not to confirm that a strategy works, but to test whether our assumptions can survive contact with realistic historical conditions. A useful backtest should be faithful to the reality we expect to face in live trading. That means paying close attention to timing, trade execution, transaction costs, liquidity, risk management, and all the small implementation details that can change the outcome. We also work with multiple backtest engines because different tools embed different assumptions and behaviors. Understanding those assumptions is part of becoming a better researcher. A critical point is that predictive accuracy and model scores are not directly tradable. Model score still needs to be translated into a signal, an entry decision, a position size, and an exit rule, and of course a portfolio construction process. Each of these choices can have a large impact on performance. We therefore spend time on how to evaluate not just models, but strategies. We discuss techniques such as deflated and probabilistic Sharpe ratios, minimum track record length, multiple testing corrections, reality checks, and methods that account for the similarity or dissimilarity of the strategies being tested. Position sizing is another major design choice. It takes us from the question of what to trade to the question of how much to trade. We cover several sizing approaches and study how they affect strategy performance on the case study data. In the course, you will implement and compare these approaches yourself. Trading costs are equally important. Very often, the gap between paper alpha and realized returns is explained by costs. So we look at implementation shortfall and decompose costs into components such as spread, market impact, latencies, and explicit fees. The goal is to estimate these costs before deployment and to incorporate them into the backtest. That way, we can ask whether the strategy has a realistic chance of surviving the costs it will face when traded live, especially as capital scales. A new and more prominent part of the third edition is risk management. We look at different sources of strategy risk and how to manage them in practice. That includes volatility targeting, stop losses, trading stops, take profit rules, position limits, exposure controls, and rules for when to reduce or shut down a strategy. The broader point is that the model should not only help us to decide when to enter a position, it can also inform when to exit, when to reduce exposure, and when the strategy is no longer behaving as expected. After we have iterated on the strategy and built confidence in its performance, we turn to deployment. One of the core principles is that the backtest and the live strategy should use the same code base as much as possible. What you test should be as close as possible to what you run. We discussed the path from research to paper trading, then to limited capital deployment, and eventually to full live trading. We also cover what happens after deployment, how to monitor the strategy, diagnose performance decay, detect drift between the backtest and the live implementation, and decide whether a decline in performance is temporary or evidence that the strategy needs to be changed or even retired. In the course, you will not just absorb concepts, you will apply them. You will work with at least one of the case studies or with your own data. You will start from a baseline strategy and learn how to diagnose opportunities for improvement. From there, you will design experiments to test whether specific changes actually improve the strategy. The goal is to learn how to do research on an ongoing basis, not just how to study formulas, write code, or reproduce an example, but how to analyze strategy performance, identify strengths and weaknesses, form hypotheses, test interventions, and evaluate whether the evidence supports the change. At the end of the course, you will present your results in a one-on-one review with me. We will discuss what you learned, what worked, what did not work, and what the next research steps might or should be. Given where we are today, the course also pays close attention to coding agents. We discuss how to use them productively without allowing them to introduce methodological errors into your research code. The book comes with more than 60 coding agent skills that encode key concepts and implementation rules from the workflow. These skills are designed to help agents stay on track when dealing with issues such as look-ahead bias, leakage, time series cross-validation, transaction cost, backtest assumptions, and deployment logic. The purpose is not to replace your judgment. It is to make you more productive so that you can spend more time on analysis, diagnosis, and research design, and less time on repetitive implementation work. The third edition contains a large amount of new material. The second edition had around 150 notebooks. The third edition now has more than 400, also driven by the case study material. It also includes more than 120 primer articles that cover foundational and advanced topics along with the coding agent skills I mentioned earlier. The second edition repo has become quite popular with close to 20,000 GitHub stars and still growing. For the third edition, we also provide 6 new libraries that implement the workflow from data sourcing through research, backtesting, evaluation, and live deployment. These libraries are used throughout the course, so you will have the opportunity to learn how to work with them directly. The next cohort for research to production starts on July 6th, and enrollment is open until Friday, July 3rd. The course runs for 8 weeks. We will have 12 hours of live instruction with one 90-minute session each week, plus bi-weekly office hours. You will also receive support throughout the course as you build your final project from day one to the final review. The aim is that you leave the course not just with a better understanding of machine learning for trading, but with a working research process, a stronger strategy, and a practical path for continuing the work after the course ends.